Thanks everyone for joining today for the new edition of the Quantum Spain online seminar. So today we're very happy to have Robert Huang giving us a talk. He's currently in Caltech, but he's also previously worked at Google. And so Robert, considering how young he is, he's like a very accomplished quantum scientist, and he's done a lot of work in topics relating to how we interact with quantum systems, with complex quantum systems, and how do we extract information efficiently from them, and what to do with it, and also things having to do with machine learning, which I believe is going to be more close to the topic of today's talk. So I guess what's going to happen is that for questions, you can write them in the chat during the talk, and I will relay them to the speaker, and then at the end of the talk, there will also be a chance to ask questions in the chat also. With that, please, Robert, go ahead. Thank you.
Yeah, thank you so much for the introduction and for the invitation. I'm Robert, and today I'll be talking about generative quantum advantage. This is joint work with Michael Broughton, Norhan Essa, Harman Navin, Ryan Babouche, and Jerry McLean. So as you might have heard, generative models have been extremely popular in the machine learning and also the broader community or the entire human society right now. One example of one of the most famous generative model is ChatGPT, but there's also a lot of other competing models such as Gemini from Google, Claude from Anthropic, DeepSeek, and also XAI, Grok, Mistral AI, etc. So what are these generative models? I think many of you have probably already interacted with them, but an informal definition of a generative model is a model that can learn from some training set such that it can generate new outputs based on the given input from some unknown probability distribution. So first of all, there will be some unknown probability distribution. One can think of that distribution in the context of these large language model as the distribution over human languages. So the input would be some questions or some statements that we state in terms of human language, and the output that we would like to sample from is essentially for example, the answer or the follow-up kind of words after these inputs. So in generative model, there's typically some training set that we would like to collect. These training sets tell us for a given input what should be the correct output, etc. And what we want a generative model to do is, after learning from these training data set, given a new input, it can produce the output based on the learned probability distribution. So for example, in LLM, what people often do is they essentially collect all the internet data, and they would just set up data set on their own. So what they often perform is that they will take, for example, a bunch of text and then ask the model to predict what is the next word. So this next word prediction is often known as language model. And these large language model are essentially just a very large scale version of language model. And as we have seen, by doing so, they somehow have emergent intelligent capabilities. So more precisely, a generative task is that we're given a data set of xi, yi that is sampled from some unknown probability distribution, p of y given x. And then what the model has to do is to learn to generate new output y for any given input x. So that's the generative task that we often consider. And building on this notion of generative models and generative machine learning tasks, one can essentially consider a notion of quantum advantage that focuses on generative modeling. So that is a notion that have been considered in the literature. I wouldn't say it's the first time that we define such an object, but we give it a very concise name. We call this a generative quantum advantage. And what this generative quantum advantage means is that we have a quantum computer that can learn to generate the desired outputs that either uses reduced sample complexity compared to classical computer. So note that in the notion of sample complexity means that it can use a much smaller training set to generate the same output, or with the same number of samples with the same training set, we want the quantum model to be able to generate outputs with higher accuracy. It can learn the underlying distribution more accurately. Or in the context of having the same training set and also achieving the same accuracy, we want the quantum machine to be able to do that, perform the generative learning using either faster learning time or faster generation time. Or it can just produce outputs that are infeasible for classical computers. So any of these aspects, we will consider them as generative quantum advantage. In a very high level, it just means a quantum computer can learn to generate outputs better than classical computers. So the notion of better can be, as defined here, captured by either talking about reduced sample complexity or higher prediction accuracy, or faster learning, or it could be faster generation, or it could be producing outputs that just cannot be produced by classical computers. So these are, this is the main aim for today's talk. So after defining this notion of generative quantum advantage, we can immediately ask the next question, which is how to achieve generative quantum advantage. So that's going to be the main question of today's talk. Are there families of unknown distribution P of y given x that maps classical inputs to classical outputs? So input is x, output is y, such that the following three criteria hold. The first one is that we want the quantum computers to be able to efficiently learn from few samples. So few could mean, for example, polynomial or linear number of samples. We also want the quantum computers to be able to efficiently generate new output. So given an input x, it can efficiently generate y according to P of y given x. And finally, the third criteria is that we want the classical computers to be unable to do the two above. So it is unable to efficiently learn and generate new outputs. For example, it cannot do that in a reasonable amount of time. So that is the main question we would like to answer. And to move towards that, what I'm going to do is to go through these three parts. So the first is I'm going to talk about generative quantum neural network, which is a model that have been proposed in the literature and have been studied for the past 10 plus years. And I'm going to talk about what are the challenges that people have faced in manipulating, training these generative quantum neural networks. And then in the second part, I'm going to talk about one of our recent theoretical results that was in stock last year, showing how one can efficiently, or repurposing them to show that how one can use that to efficiently learn any generative QNNs, essentially addressing the challenge that people have faced previously. And the third part, I'll talk about a series of experimental results that we demonstrate, that was used to demonstrate generative quantum advantage using these efficiently using these efficient learning algorithms for generative QNNs. So let me begin with the first part on generative QNNs and challenges. So recall that the task is we're given a data set of xi and yi, sampled from some unknown conditional probability distribution, and the goal is to learn to generate new y for a given x. A generative QNN proposed in the literature can be broadly thought of as the following. First, given this input x, they would have some way, it could be a trainable way or just some fixed way, that encodes it into a quantum state psi x. The encoding can be extremely simple. We can think of x as being, for example, just some bit string. So in that case, the quantum state can just be a computational basis state associated with that bit string. We can also encode x into the measurement basis. So we will essentially come back later. So after having these quantum states ix, one would apply some quantum circuit, C beta. So beta is some parameter. It's a high-dimensional vector. It's not the inverse temperature, just some high-dimensional vector to the state ix. And then we will measure the output state of this trainable quantum circuit in the measurement basis mx to sample y according to kind of a parameterized conditional probability distribution, P of y given x and also beta. So that is the notion of generated QNNs that people have studied before. It's not hard to show that if one consider an expressive enough quantum circuit, C, then a generated QNN is universal. So it's universal in the sense that for any conditional probability distribution, P of y given x, there's always a choice that one can make on this quantum circuit C such that this QNN model will approximate any of such conditional probability distribution. So this is similar to how generative classical neural networks are universal in the sense that as long as they're big enough, then they have the capability to learn any probability distribution. So the same also applies here for generative QNNs. In a way, that means that they're kind of a reasonable model, because if they're too restricted, then they're not so reasonable. However, that doesn't say anything about quantum advantage, because in terms of universality, generative classical and quantum neural networks are equally powerful. In the previous literature, people have also focused on a variant or a more restricted version of generative QNN known as generative shallow QNNs. They're essentially just quantum neural networks or trainable quantum circuit or parameterized quantum circuit with constant depths. So because of their constant depths, it seems like they're quite simple and they're quite limited because they can only generate entanglement that are highly local. But despite their simplicity, they're actually surprisingly powerful. So in prior work, for example, architectures for quantum simulation showing a quantum speedup in PRX, enclosing gaps of a quantum advantage with short-time Hamiltonian dynamics, published in PRL, both of work I'm not involved in, they have established the computational power of shallow QNNs. Basically, under a standard complexity theoretic conjecture, one can show that there are shallow quantum neural networks that can generate distributions that no polynomial time classical algorithms can generate. Even though they only produces geometrically local entanglement, shallow QNNs are actually very powerful. So here's a figure from our paper that illustrates this in more detail. So if we look at a two-dimension shallow QNN that is given in this figure to the left, where what this 2D shallow QNN does is very simple. It just start with Hadamard everywhere, followed by CZ gate between these edges, followed by RZ, so Z rotation on each qubit, followed by a Hadamard everywhere. So that one should think of this as time is flowing out of plane, so it's flowing outward. And in this circuit picture, one can see that this is just a 2D shallow quantum circuit. One can think of these RZ as having the parameters, so they're trainable and they produce this shallow QNN. However, if one put in an all zero state and after that measure everything in the Z basis, one can show that this actually corresponds to sampling from a one-dimension deep quantum circuit and also generating bit string from this deep quantum circuit. I will not get into the detail, but essentially what happens is that this edge of this rectangle now get mapped into kind of the spatial dimension, but these other spatial dimension in this 2D lattice now get mapped into the time dimension. So in this case, in this figure, time is flowing upward. And essentially what happens is that all of these RZ gates, they get essentially mapped back into here. But then other than that, there will also be a bunch of Hadamards that get injected. So together one can see that this is really a universal 1D quantum circuit in the sense that any quantum circuit that one would like to write down can be written as a form of this by choosing the appropriate RZ rotation. So this is a mapping that one can show using ideas from measurement-based quantum computation. Essentially, it's because when we perform measurement, these CZ gates that are placed here will now act as this kind of teleporting, act as entanglement that allows quantum teleportation. So after this layer of gates, when we perform measurement here, it essentially causes the state to get mapped to, or the state here to get teleported to the next layer. And then again, you get teleported to the next layer and so on. So when we unravel this teleportation, we can obtain these 1D deep quantum circuit. So together, performing a measurement on this 2D shallow QNN, one can show that it's equivalent to essentially sampling some 1D deep quantum circuit, and then also getting one measurement outcome from them. And then essentially relying on some standard complexity theoretic conjectures, such as polynomial hierarchy doesn't collapse to the third level, one can show that classical randomized algorithm with post-selection capability is not equal to quantum algorithm with post-selection capability. And as a result, if one can simulate, if there does exist a polynomial time classical algorithm that can simulate these randomly sampled 1D deep QNN, one can show that randomized classical algorithm with post-selection capability can simulate any quantum circuit with post-selection capability. And hence, it will cause polynomial hierarchy to collapse to the third level, and that will violate the standard conjecture that polynomial hierarchy should be an infinitely high power. So using this, one can essentially prove that there are shallow QNNs that can generate distribution that no polynomial time classical algorithm can. So this is the formal proof, but in a very intuitive level, what essentially happens is that when we perform measurements on the output of a 2D shallow QNN, it essentially causes entanglement to start growing. So there's like these idea of entanglement swapping. Essentially, when we perform measurement here, it will cause the entanglement to get passed down. So even though this is a 2D shallow QNN, underlying it is actually running a random 1D deep quantum circuit. And as a result, it can generate distribution. For example, the distribution coming from these measurement outcome, which is equivalent to the measurement distribution for these guys. They will be highly correlated. It will be highly non-local, and it will be correlated with all of these other guys. And as a result, they are classically hard to sample from. So that's the idea. So this is just a review of what was known in the literature.
So one question now you see this. In the left hand side for the 2D shallow circuit, do you have to do something adaptive?
No.
No. Okay.
Yeah. So if one does it adaptively, then this 1D deep QNN, it will be really one can essentially pick arbitrary deep QNN. So here, if one doesn't do it adaptively, so one just measure everything in a single shot, like measure all of it. So it's really a shallow circuit, because adaptive measurement, it's kind of not shallow, because one needs to perform measurements and then followed by that. So here this is really a shallow thing. So we should just measure everything and now get this bit stream. Even then, it's still powerful, and the reason is because in that case, what happens is that one will be randomly sampling a deep QNN and then measuring from it and then sample from it. So one cannot control which deep circuit one will be implementing. It will be randomly drawn. So that's the main difference between kind of in a more standard measurement-based quantum computation. One needs to do things adaptively. Here we don't. Everything is non-adaptive. We just kind of measure the whole thing out, so it's very shallow. But that is already classically hard to simulate because of these kind of post BPP not equal to post BQP and polynomial hierarchy doesn't collapse kind of thing.
Yeah. Okay. Nice. Thanks.
So the power of generative shallow QNNs have raised the hope of using them to achieve generative quantum advantage. As we can see, because generative shallow QNNs can generate distributions that no classical algorithm can achieve. And as a result, there have been an extensive number, I would say hundreds or even thousands of papers that have studied the problem of learning and training these shallow QNNs. Unfortunately, prior to our works, including the recent experimental work and also the previous theory work, no efficient learning algorithm was previously known. And one of the biggest reasons behind this is that the landscape was extremely bad. So here is a landscape plot that we actually calculated by just taking some shallow QNNs and just taking a 2D slice of it. So shallow QNNs, they're well known to not have barren plateau. So barren plateau means the gradient of this landscape is exponentially small. So basically it's completely flat and there's no way to train them. However, shallow QNNs have some variant of barren plateau, as one can see from this figure. So here, this is just some 2D slides, and we kind of artificially assume that we have, or we just assume that we have already found the true minimum, which is this tiny point in this middle. And then we just take some random direction to random direction and just start moving out and look at what the loss function looks like. And as we can see, this looks extremely bad. So if we move out slightly, it quickly, here's a zoom in. If we move out slightly, quickly go up, and then suddenly it start fluctuating. Start fluctuating in a very random pattern. So if one look at it here, it's just completely random. So even though it's not exponentially flat, so we can do gradient descent, we'll still not go to the true minimum. We'll just get stuck in these local minima, can try to jump out and get trapped into another local minima. And in this paper, in this experimental paper, we also have, or in this most recent paper of generative quantum advantage, we also did a very precise theoretical analysis showing that this landscape, even for a very simple like depth 3 shallow QNN, they would have exponentially many suboptimal local minima. Suboptimal in the sense that it's just very, very high. It's a very bad model. And also each of these local minima, if one just kind of expand out with an exponentially large volume, one can prove that each of these suboptimal local minima is actually the true minima, like the true global minima within that region. But it's not the actual global minima in the entire space. And what that means is essentially they're not just bad local minima, they're also an attractor because they're really the optimal point within a very big exponentially large volume. So if we start from there and start to gradient descent, we'll just run into those very bad points. And some of these aspects, so we did a much more careful analysis of this, but some of these aspects has been observed in previous work because when people try to train these shallow QNN, as number of qubits grow, they start running into trouble. Like the training times start growing exponentially. So even though these shallow QNNs themselves can have powerful computational ability, they cannot train them. And because gradient descent and other methods, they just get stuck in these bad local minima and fail. So if we go back to these previous questions, we can see that first, because these shallow QNNs, they're very shallow, quantum computers can efficiently generate new outputs. So that criteria is checked. We also know that using pH doesn't collapse, classical computers cannot efficiently generate new outputs. So that criteria is also checked. But from these landscape challenges, we can see that quantum computers, it's not clear that they can efficiently learn from few samples, which raises this existential question that are generative QNNs just fundamentally hard to learn as the price to pay for their beyond classical power. So what I'm going to do next is to show how one can actually efficiently learn any generative QNNs by using a very interesting trick that we found. So what we call that is, we call this trick parameterization by local inversion, but there are actually many variants of this phenomenon and this technique that were used, that one can use it for. And so given an n-qubit unitary U, we say V1 is the local inversion of U for qubit 1 if when we compose U and V1 together, they becomes identity on the first qubit after composing them. We can similarly define V2 to be local inversion of qubit 2, which when composed with U, they become identity on the second qubit. So an important fact that we're going to use is that given an n-qubit unitary U, their local inversions, V1 all the way to Vn, uniquely determine U. So if one think of these local inversions as like, in the context of states, as local reduced density matrices, then we know that this is not true. However, for unitary, and if we focus on local inversion, then one can show that this is indeed the case. And the proof is extremely simple, and here's a graphical proof of this phenomenon. The idea is that with the knowledge of these local inversions V1 through Vn, there's already a very simple way that we can suit them together to form the n-qubit unitary U. And it operates as follows. So we start out with having two n-qubits sitting here. We imagine that on the maximum mixed state, there's this true unitary being applied. So note that applying U to maximum mixed state is still the maximum mixed state. And as a result, having these U or not is the same. So in the physical space, it's the same. So this U, we should think of it as it's just living in our imagination. So now what we do is we now utilize these local inversion to try to essentially turn this imagined unitary into an actual physical reality. So the way we do that is we compose U and V1, which uncovers the first qubit. As we said, it becomes identity on the first qubit. So what we can do is we can just throw it away, just remove it, or we can maybe swap it out and then just put it there. And neglect it. So now we have one less qubit. We then rewire it. So we take the first qubit of the arbitrary input state psi, rewire it back, and then implement V1 dagger. So note that in the unitary space, all we have done is we have U followed by V1, followed by V1 dagger. So that's just U. So that allows us to heal it back. And as we can see, by going through these 6 steps, we have removed one of the qubit maximum mixed state and essentially rewire psi into U. So if we just keep repeating that for, say, the second local inversion, the third local inversion, and so on, we have essentially we can turn U from just in our imagination into physical reality and can be applied onto arbitrary input state psi. So if we forget about psi, we just think about this all of these construction as a unitary transformation. Then we have essentially implemented U by combining these local inversions. So now the idea is very simple. So utilizing these new parameterization of a unitary, what we will do is we're going to train and learn an n-qubit generative QNN by training and learning the local inversions V1 through Vn instead of training U itself. And so if we now go back to this optimization landscape, actually we can prove this rigorously that if we now, when we previously trained generative QNN by optimizing these parameterized quantum gates, we see that the landscape is extremely bad. But when we train generative QNN by optimizing, or generative shallow QNNs, by optimizing these local inversions of the QNN, one can prove that because these local inversions for shallow QNNs are essentially just a constant local object, and they only have, say, a constant number of parameters. One can also prove that the landscape, because of some continuity phenomenon, the landscape is going to be extremely nice. There's not going to be too many local minima, and as one can see from this figure, essentially there's just this big chunk of global minima. So if we just start from some random place, one can prove that it would always converge to a true global minima for each of these local inversions. And as a result, the entire learning and training process can be proven to be efficient. So here's a more detailed plot. So this is the standard landscape that we see, but now in 2D figure. This is the 5x zoom in onto the global minimum. We can see this is very reminiscent of this barren plateau kind of picture, even though it's not strictly a barren plateau. And on the other hand, if we utilize these local inversion parameterization, we see that the landscape is much nicer. Here's the 4x zoom out. Essentially, because it's the entire parameter, like we're just in a compact manifold for this training procedure, it would actually loop around. So this is what we see in this stripe pattern. The stripe pattern corresponds to essentially, because we're looping around, this kind of constant size landscape. And here, this is the probability of successfully finding the global optimum when we start from a random point, when we scale the number of qubits. As we can see, for standard parameterization, the probability of success decays exponentially. Note that even when we approaches around 20 qubit, it still works okay. So some of the previous work kind of just go to 20 and then say it works. But actually, if you scale up a little bit more, one can see that the probability of success really decays exponentially, and is effectively zero when we go to above 60 qubits or above 100 qubits. And actually, in order to achieve quantum advantage, we need to go to these big system size. And actually, for these shallow quantum neural networks, we need to go to even larger number of qubits in order to actually achieve quantum advantage. On the other hand, if we utilize these local inversion parameterization, we can either use it as, when we say individual, it means we just have local inversion for each individual qubits. Blocked means essentially we have local inversion for blocks of qubits. So the aim is to kind of optimize a block altogether. We can see that when we go to a block setting, the probability of success is around, it saturates around 80. But if we focus on purely local inversion, we can see that it has the probability of success very close to 1. And that essentially is just a numerical kind of evidence or numerical verification of the theory that we have established. So broadly speaking, we can establish the theorem that says any unqubit generative shallow QNNs can be learned in polynomial time. So it's polynomial in the system size as well as polynomial in the inverse accuracy, such that for any input x, the output y can be sampled accurately up to epsilon error. So here, the error is in terms of the total radiation distance. So the output y can be sampled accurately up to epsilon error in terms of total variation distance. So using that theorem, we can establish generative quantum advantage as a corollary. That is, there are families of unknown distributions mapping classical inputs to classical outputs. These unknown distributions are essentially a distribution generated by these shallow QNNs, such that because they're shallow, quantum computers can efficiently simulate them and generate new outputs. And furthermore, using the previous theorem, quantum computers can efficiently learn from polynomial number of samples. On the other hand, building on existing computational advantage of shallow quantum circuits, we can prove that classical computers cannot efficiently generate new outputs. So together, that establishes generative quantum advantage for learning to generate classical outputs from classical inputs. So for the final part, I would like to present various experimental results based on this idea. So what we do here is we're going to focus on training or using a 3-dimensional shallow QNN. The figure that I showed previously is a 2-dimensional one, but we can easily generalize it to 3 dimensions. We're going to use this mapping that I described to map 3D shallow QNN into 2D deep QNN. And then we're going to utilize Google's Sycamore quantum processor to generate new output Y using these 2D deep QNN. So somehow surprisingly, in the physical world, it is slightly easier to generate deeper QNN, not too deep, but deeper QNNs due to like the kind of the experimental setup that we have. So this is a device layout for this experiment that we're going to run. We're going to utilize 68 qubits on this 2D geometry. Each of the crosses are the qubits, and each of these diamonds corresponds to the CZ gates that one can implement on this Google's quantum processor. Actually, some of our experiments were done a bit of a while ago, so like last year. So we're using Sycamore. Some were actually using this newest chip, Willow. So there's some experiments are that, and some are the later one. And the first plot here corresponds to how many training samples do we need in order to achieve what is the error. So here we're showing essentially as the number of samples increases, as the theory suggested, the error will decrease very quickly, as we can see here. So if we go to around 10 to the 6 number of samples, we can already achieve an error that is less than 10 to the minus 3, which is around what the currently available machine precision are. So the current gates that people can implement in the lab also only have an error value around 10 to the minus 3. So below that, we're essentially perfect. And here are the experimental demonstration, which included both new data collected for smaller shallow QNNs, as well as taking or kind of a new data analysis based on Morvan et al.'s paper published in Nature last year. So if you look at this plot here, we're essentially showing the XCB score as the number of shallow qubits increases. We plot 3 results from quantum experiment. The blue one corresponds to the trained one. The star the yellow one corresponds to the ideal case. So we're not doing any learning. We're just taking the true ideal case and just running it. We can see that the learned quantum neural network matches with the ideal one very well, because as we have seen, the error value is already very small. We also consider using the same exact structure, but forcing the RZ gate to become Clifford. And that allows one to essentially calculate XCB for a much bigger system size, so that we get to see what is happening. So that's the purple line. And we can see that for the Clifford one is slightly above. The XCB is very close to the learned quantum neural network as well as the Clifford one. So we can expect that when we did generate samples for the learned quantum neural network at this large size, but calculating the actual XCB is going to be hard. But we can use this Clifford simulation, or this Clifford QNN, to get a sense about what that looks like. And here, this is quantum simulation. So because quantum simulation of the learning process, as well as the generation process and the evaluation, we can see that in this case, the performance is almost perfect, since there's no noise. So the reason that XCB still decays as the number of shallow qubits grow is because of noise. However, we can see that even in the presence of noise, we can still achieve advantage over standard or state-of-the-art classical generative models, such as transformers, which is commonly used in these LLMs, or XGBoost, which also can perform quite well in these more kind of discrete generative tasks. So in this figure, we're just looking at smaller shallow QNNs and comparing with state-of-the-art classical generative ML models. In this other plot, we're comparing with sort of essentially the best known classical methods that tries its best to simulate these QNNs using a variety of tensor network techniques. And one can essentially perform an estimate of what happens when we utilize these these models to achieve different performance. So if we utilize the frontier supercomputer, which corresponds to running it for 1 minute, which corresponds to running 10 to the 20 floating point operation, which is huge, we get to achieve an XCB line that looks like this. So the reason that it has a sharp decay is that because of the bounded computational time, it has to do a lot of approximation for larger sizes, and hence this has a sharp decay as one meets a certain threshold. But below that threshold, they can perform perfectly. So they can achieve an XCB score of 1. We also consider this red line, which corresponds to running the frontier supercomputer for essentially 18,000 years. That corresponds to 10 to the 30 floating point operation, and we can see that it gets to achieve perfect XCB for longer, but then also quickly drops. Here we showcase the quantum experiments that we can obtain by training these shallow QNNs and then applying it. We can see that this also has a decay because of noise, but at around this point, when the corresponding shallow QNNs is around 35,000, which still get mapped into these 68 deep 2D QNN. So this is shallow QNNs in 3-dimensional space that has a huge number of qubits, but it can map into a much smaller, like around essentially 68 qubit, but deeper QNN, which is what we simulate, or which is what we run on a quantum device. We get to see that at this crossing point, we can essentially obtain, or beyond this, we can obtain quantum advantage in learning and generating classically hard distributions. So that provides an experimental demonstration for generative quantum advantage. And there's actually another different application, which is in compressing dynamics. But we can also establish, we have also established generative quantum advantage for the task of compressing physical dynamics. The idea here is very simple. Suppose that we have some very deep circuit that we would like to run. Maybe this circuit was generated by doing a trotterization of some Hamiltonian dynamics that we're interested in. And this is the target unitary that we're interested in. What we would like to do is we would like to essentially have a quantum generative model that generates, by taking this as input, doing a bunch of learning, to generate a low depth circuit backend that is a good approximation to the target unitary. We can also show that in order to perform this compression task, there is generative quantum advantage, because this will be in general classically hard, but quantumly easy. And furthermore, we can essentially achieve this task using the same theorem that I described earlier, using these generative QNNs. So the idea is very simple. All we do is we take these shallow QNNs, decompose them into these local inversion pieces, and then we will train and learn each of these local inversion pieces by essentially taking the target unitary and training these pieces so that it locally inverts the qubits to become identity. And now afterward, we can then just take these local inversion pieces and then combine them together to form the final trained QNN. So here, this is a more compact visual representation of this algorithm that I described earlier. So one should note that the dagger of it is the local inversion. So we're running some local inversion. We swap it with some ancilla, essentially just swapping out the qubits. And then we implement the inverse of the local inversion, which in this case is just U2. We can structure them in such a way that the resulting quantum circuit is still shallow. So as system size scales, we should think of it as we would just do U2, U4, U6, U8, and so on. On the second layer, we have U1, U3, U5, U7, all done in parallel. So now afterwards, what we have done is we can decompose these shallow QNN into pieces, train each of these pieces. Now we combine them to form a trained shallow QNN that uses some ancilla qubits. And we implement that by compressing 20 qubit, very, very long time dynamics. And the way we map it onto our device is by essentially considering the system qubits as this dark blue line, and then Scylla qubits for each of the system qubit as this purple points. And some qubits remains unknown because we don't know how to fit them. And here we showcase the result after training. So we consider some very, very deep 20 qubit unitary that corresponds to a very, very long time Hamiltonian simulation, Hamiltonian dynamics of some local Hamiltonians. However, we focuses on Hamiltonians with MBL phenomena, many-body localization phenomena. So the entanglement basically, so the entanglement is growing very, very slowly. So even when the time becomes extremely long, like 20,000s or higher, there always exists, there still exists a shallow quantum circuit that can efficiently simulate this dynamics. On the other hand, if one just creates trotter simulation or a quantum circuit for doing the same calculation, it will generate a very, very deep quantum circuit. But now we can just essentially compress it all down into a very shallow circuit, exactly look like this. The number of the depth is very small, and as a result, we can implement these very long time dynamics using a noisy quantum computer, and that's the results shown here. So we can see that the raw data is already performed pretty well. We now do a bit of error mitigation, then now that's almost perfect with the ideal result or kind of the observable expectation value for the ideal case. So we have look at that for qubit 3 and qubit 16. All the other qubits also perform pretty well. So to conclude, in this work, we have closed the loop on generative quantum advantage. So note that previously it's known that there are efficiently generatable distributions that are classically hard. However, the learning part was previously a challenge. In this work, we close this loop by showing that there can be an efficient learning and generation of classically hard probability distribution, demonstrating generative quantum advantage. And furthermore, the experiments supported this advantage over classical generative models, such as transformers, using up to 800 effective shallow qubits that were implemented using 70 physical qubits in the experimental lab. And that's it for my talk. Thank you so much for listening.
Great. Thank you so much, Robert, for the super nice talk. There's some clapping in the chat. Yeah, so for everyone, please, if you have questions, ask them in the chat now. Or maybe if you raise your hand, maybe, I don't know if the admins can also allow you to speak, but in principle, maybe write them in the chat.
Yes. No, we can unmute if somebody raises the hand.
Okay, somebody wants to talk, we can unmute them, yes. Okay, but, so maybe, while people think of their questions, I have, well, I'm going to take the privilege as chair to ask one or two, maybe. So this last thing you said, I think is very interesting, because what you're saying is that you can compress, well, you have a method of compressing, well, long-time dynamics. But I guess you here, in order for this to work, you have the promise of, well, you need the promise that this circuit actually exists, right?
That's right, of course,
so
yeah.
That's what you're using.
And of course, it's not possible to find.
Yeah, so I don't know if you know this, there's this idea that from at least I know from a paper of Dorita Haronoff of fast-forwarding quantum Hamiltonians.
Yes.
That somehow this is related to being able to do phase estimation with, very efficiently.
That's right.
Do you think this is a way of, I mean, I don't know, what does this mean for that?
Yeah.
Can you also use these circuits to do this phase estimation, for instance, or I mean, what's
Yeah, I mean, there are different things. I mean, from that paper, one of the key results was that there are Hamiltonians that cannot be fast-forwarded, so they're not compressible. So if it's like time of t, then there's no way to compress it into sublinear in t. Or maybe much smaller, let's say. So in those cases, this method will definitely not work. But people also identify cases where this does. Like there are some methods that can be fast forwarded, and this could provide a way for kind of a machine learning approach for doing that. So instead of humans just kind of thinking about it and try to construct circuit, we can also just run this algorithm.
And can you also use this method to actually check whether a Hamiltonian can be fast forwarded? As in, you come up with a unitary with this method and then see how well it works, or?
Yes, I think so.
Okay, that's interesting. Yeah, that's interesting because this principle of fast forwarding or not seems to be related in some way to quantum chaos, right, or to ergodicity. So maybe it's a nice way to characterize it. Yeah.
Yes.
Yes. And the other question I have is actually about the experimental data, because you have a very large number of qubits.
Yes.
How is that possible? How is that work?
It's related to what I said here. So what we do is we focus on 3D shallow QAnon. So you should think of the 3D as the following: is that on one edge it's 68 qubits, but on the other edge there's a huge number of qubits on kind of the third spatial dimension, and and essentially what we do is we, after training these 3D shallow QANONs, we'll try to kind of first utilize what I talked about earlier a little bit to map it into a 2D deep one. So initially it's just a 3D shallow one, so 68 on one face of the 3D lattice, but then much higher on the other face. And then what we then do is we will then map it into a 2D deep QAnon and try to compactify it back into one that can be implemented on the quantum processor. So that's why so in a physical reality, what we do is we still implement these 2D deep circuit at depths that kind of saturates what's doable on the current quantum processor.
Interesting.
So that's why I emphasize this shallow qubits. It means the number of qubits in a kind of the shallow QAnon. But in a way, one should really think of this as kind of more like the volume, like the space-time volume of the quantum circuit.
Right. So I don't know if 68 is okay. So it's so from 68 you sort of have a bigger one.
Yes.
Yeah. Are there any questions from the audience, either in the chat or Javier? Yes. You're muted, Javier.
Sorry, I was muted. So very nice, Robert, and really very exciting results. I mean, every time there's this claim of there are claims of advantage. Nobody talks about supremacy anymore. But there's always this kind of excitation from the classical side. So I was going to mention to you if you're aware, there's a company called Multiverse Computing. And they claim to have, actually, I don't think this is published because they're a company, but they rose a huge amount of money last month because they claim to have been able to compress LLMs to a ridiculous size. So, I mean, you showed us a theorem claiming advantage. I don't know what the premises are. I don't know if you're aware of this, or whether tensor network techniques would be encompassed by the theorem that you showed us before.
So I guess there are a few questions. The first is these theorems rely on widely accepted conjecture. So for example, polynomial hierarchy doesn't collapse. Computer scientists have been thinking about that for many decades. That's one of the, because people are hoping to understand whether P equal to NP or not. So I would say that is much more on a very solid footing. And of course, that's still a conjecture because we don't even know if really quantum computing is more powerful than classical computer from a truly rigorous standpoint. But I would say this is very hard to violate. Like if one could essentially show that this conjecture is false, then that will imply a huge amount of crazy implications that are beyond quantum computing. So I would say that these theorems are more reliant on these much more kind of rigorously tested and people thought very hard about kind of conjecture. I mean, I would say most people would consider those conjecture to be similar to assuming that P is not equal to NP, and which I think most people believe. And otherwise, there's not going to be cryptography, and there's no privacy, and it will be a very
Thank you.
Yeah.
But, okay, thank you. That's fine. I think I don't know if anybody has another question.
No one's asking questions in the chat. It seems.
Well, then I have a second, if you don't mind.
Sure. Yeah, go ahead.
Yeah, I mean, it's concerning this compression. This awesome. So maybe you're aware because you worked at Google that there was this paper which I think Google is not extremely proud about, which is the one that claimed to have found evidences of teleportation due to a wormhole. It was, so this was done with 7 qubits, and it was optimized using also some machine learning techniques in order to tailor the. So I don't know if you, I mean, if you're not aware of this work, but the question is, with your techniques, do you think this could be enhanced, or this SYK Hamiltonian is not of the kind that could be compressed and pushed to higher number of qubits and higher?
Yeah, I am aware, because one of my close collaborator, Tommy Schuster, has been it has took a very deep dive into that wormhole paper by Google. I would say the problem there is that when they're compressing, they're actually dropping some important physical phenomenon in these SYK model. Like they're compressing so much into such a small system, such a simple Hamiltonian, that actually some important physics or some important kind of signature of black hole physics and quantum information scrambling were actually dropped. So I would say in that paper, they're compressing too much. They're compressing too much so that they're, in a way, I would say the community think they're not really matching the wormhole physics anymore. It still captures some of it, but a lot of other important ones are not there, which is what was showcased in kind of a follow-up work by Tommy Schuster, Norman Yao, and others. So I would say this compression that I'm talking about here, it will generate a shallow circuit that is like just truly close to the unitary U. So it will be close or a very strong quantum information distance or quantum or like this kind of distance sense. So so I would say if one uses this to do compression, one will still retain all of those features. But of course, what that means is also the compression cannot be that much, because we will still be capturing all of those features, so the compression cannot be as powerful. But I would say we still need to see, like, for example, if we take SYK model and then do this, how much we can compress it. I think that's an interesting follow-up question to explore.
Okay, I hope this is in your agenda. I mean, I'm really excited. Thank you.
I guess any last questions from the audience? Seems no one's raising hands. Okay, so in that case, shall we leave it there for now?
Yeah.
So thanks everyone for coming, and especially thanks Robert for the super interesting talk and results. Yes.
Yeah.
Thank you so much.
Thank you very much.
Thank you very much.
Stop the recording now, or?
Yeah, Alberto will do it. Yeah.
Okay. Thanks. Great.
Goodbye.
Yeah. Bye.
Bye.
Bye.